we're gonna start a new chapter, which is the last chapter in the semester. This chapter is about the Box-Jenkins methodology. Usually we call that ARIMA model. It's a fancy term. It's also an advanced model that incorporates several components in the model. Now, first of all, ARIMA model basically is a process. It's not really one model like we have for simple linear regression model, multiple linear regression model. We have the X variables, Y variable, we run the regression, we get the results. Or like decomposition, we have the data, we click several buttons, we get the model and the forecast. ARIMA model is a family of models in which we go through the steps and sometimes we repeat it in order to find the best model that. Now, at the very beginning, we don't want to restrict our idea to any particular pattern or any particular model. We will have a pool of models that we consider, and then we examine the data to determine which model we want to use. This model can be used for stationary and non-stationary time series. We haven't been talking about stationary, the concept, for a while, so let me give you a refresh on it. So stationary means this process is stable. It varies about a fixed level, which is usually the mean. When we have non-stationary, we see there's a process with trend. That's usually what we say is non-stationary. Okay. The ARIMA model has 3 components total. It's actually, you can tell from the name right here, ARIMA. So AR is one component, and the I is another component, and MA is the third component. For the group model, whatever data we have at the very beginning, we're going to look at these 3 components to determine for each component what parameter we want to use. Then we run the model, okay? And then after running the model, if we decide the model is good, we'll use it for forecast. If we decide we need some improvement, then we go through the process again to further determine what else we can do, okay? The first component is the AR part, okay? And the AR part stands for autoregressive. And the idea here is that since in time series data, we usually expect some autocorrelation among the values. For example, current period value is correlated with value in the previous period. So we call that like one autocorrelation, right? And that gives us the idea of running a regression model using past values as the X variable, trying to explain the current value. So that gives us this model specification. So basically the structure here is still a multiple linear regression model. The difference is that the X variable is not the traditional X variable we've seen before. The X variable instead is the prior period values of the time series itself. So YT minus 1, YT minus 2, etc. YT is representing the current period value. We want to use the past period values, and that is assuming that the previous period value is correlated with the current period value, and thus for information captured by the previous value is useful in predicting the current period value. If we believe there's autocorrelation at like 1, then we're gonna use AR1, which means we only include the value in the price period. If we have autocorrelation at like 2, that means values 2 periods prior is correlated with values in current period. And therefore, we're gonna include values 2 periods prior as the X variable and use it to explain or predict the current period value. So we call that AR2, meaning we have autocorrelation at like 2, and we included both YT minus 1 and YT minus 2, the values in the prior 2 periods, okay? And it all goes all the way to the peace period, whatever period we define to be appropriate. Then we're gonna stop there. Okay, it could be AR3, etc. That is not very common. Most of the time we stop at AR2, 3. That's pretty much about it. So that's the first component. And the second component is the I part. I'm gonna save it for the last. I want to move to the third component that I underlined previously, which is the MA part, which denotes for moving average. Now notice that this moving average is not the same moving average as we learned in chapter 4. I know it's a long time ago, you probably don't remember anymore, and we haven't visited that for a long time. But that moving average concept saying that we want to, for example, moving average 4 means we want to add the 4 values together, take the average, and we want to do that for every 4 periods in our time series. This MA here, this moving average here, is totally different. So the idea for the MA part is that since we expect for time series data when we run regression, the residues tend to be correlated, right? In last chapter, we were looking at the Durbin-Watson statistic to determine if there's autocorrelation in the residues. And a lot of times we find that's the case. Now we recognize that residues can be correlated, and therefore for the MA part, we are using the correlated residues as the predictor for the Y variable. And as you can see here, this is another multiple linear regression. In the regression, we don't have our typical X variable. Instead, we have the residues in the current period, residues in the prior period, in residues in 2 periods ago, etc. Okay, and this is used to capture the autocorrelation in the residual part. We also need to determine how many periods of residues we want to include in the model. If we decide we only need the prior 1 period before, then that gives us an MA1 model, meaning that we included the error term or the residue 1 period before. Now, if we believe there's autocorrelation in lag 2 in the residues, then we want to include both residues in prior period and 2 periods ago, and that gives us the MA2 model. And the same concept applies when we have MA3 or MA4 all the way to MAQ. Although, again, most of the time we don't go that far. MA2, MA3 is most common. MA1 is common as well. All right, so that's the MA part. And there's one component I didn't talk so far, which is the I part. The I part is called integrated. The integrated part is really just used to deal with the stationary part. Okay, if the time series is not stationary, then we need to make it stationary first, then consider the MA part and the AR part. Okay, basically the very first step is we look at the data to determine if it's stationary or not. If the data is not stationary, then we will take the difference of the data. And when we take the difference of the data, we call that I1, integrated 1, meaning we take the first difference to make the data stationary. Now, sometimes the first difference does not work. We have to take the difference again. So take the difference of the difference, and that will make the data stationary. Then we call that I2, integrated 2, meaning that we have the difference the data twice to make it stationary. Of course, this concept goes to I3, I4, but most of the time we either have I1, I2, or even sometimes I0, meaning that the data is stationary. There's no need for us to take the difference. Okay, so that's the 3 parts, the AR part, the MA part, and the I part, and all of them together consist of a family of models. In terms of the modeling, here are the steps. The first step is to postulate general class of models. Basically, at this point, we have data, we decide to use a Riemann model. For Riemann model, we have a class of models because we could have AR1, AR2, AR3, in combination with I1, I0, I2, etc. So there are many combinations that we can pick from. And the second step is to do some preliminary analysis to determine which model can be used tentatively, meaning that as of right now, let's try this model. The reason we call it tentative is because we don't know if the model is a good fit or not. Then the next step is to run the diagnostic checking to see, is the model adequate? Is it good enough? From there, if it's good, then we're done. We can use the model for forecasting. If it's not good, then we'll go back to the second step because we decide that model is not adequate. Maybe we need to do more. Then we'll go back to the second step and identify other models that we can use for the estimation. So I would like to start with an example and show you how we apply the steps, how we use this family of model to determine the best model for the data for forecasting. Okay, so the example says the Camera Consulting Corporation specializes in portfolio investment services. Lead analyst was assigned the task of developing more sophisticated techniques for forecasting Dow Jones average. Lin recently attended a workshop on Box-Jenkins methodology and decided to try the technique on the Dow Jones transportation data. Daily closing average of the transportation index on 65 days during the summer month are collected. So we have time series data on the transportation index, and we have 65 of them. So the idea is to use Box-Jenkins methodology to model the data, which is the RIMA model. The first step is to identify the model. We decided to use a RIMA model. So we have that group of models to pick from. Now we need to determine what specification we want. To determine the model specifications, we need three things. So we need to identify the I part, whether the data is stationary, and we need to determine the AR part and MA part. Okay, the first item that we need to determine turns out to be the integrated part. We want to know if the data is stationary or not, and that relies on the time series plot we see here. And I believe at this point, I do not need to go back to Minitab to show you how to do the time series plot. If you can't remember, definitely go back to the previous chapters. Okay, I also have the instruction here says you can go to graph, time series plot, and then do the time series plot. Specifically for this example, the data are not stationary. As you can tell from the time series plot, there is definitely upward trend. It is increasing over time. That means for the I part, at least we need to take the first difference to see what happens. So the autocorrelation function here also shows that there is strong trend because the autocorrelation are all significant until the fifth leg, and they are dying slowly. So that further identifies or confirms that we need to take the first difference. And therefore, the next step is to take the difference of the data. That's the integration part. I've got this screenshot here helping you to know how to take the first difference. We did this before, and that's the reason I'm staying on the PowerPoint slides instead of going to Minitab to show you. Once you take the first difference, now you want to look at the autocorrelation graph again to determine the MA part and the AR part. This is the graph we need, and we did this for the difference. Then the other item that we need is called the partial autocorrelation. In a minute, I'm going to move to Minitab to show you how to obtain partial autocorrelation. Partial autocorrelation basically measures the correlation between the current value of y and the value of y k periods before, after adjusting for the effects of all the y values between the current period and k period ago. Okay, that's why it's called partial. We want to look at the correlations between the current period and k period prior, but we at the same time want to tease out all the autocorrelation between the current period and the periods in between these two. Okay. And then once we have these two graphs, the autocorrelation graph and the partial autocorrelation graph, we can start to determine what model specifications we want, the AR part and the MA part. And here's a little table that may not be that helpful at this time. After we talk about the whole concept, when you come back to the table, it makes more sense. So I'm gonna skip this table for right now and show you this. I want to give you a general idea first before we move to Minitab. On this slide, it shows you the scenarios for AR1 and AR2. How do we determine the level for AR? Is it 1 or 2 or 3? And here are the situations. So when we see for autocorrelation is dying out and the partial autocorrelation is cutting off. And when we say die out, that means the autocorrelation is decreasing gradually over time. It could be either positive on the top here, gradually decreasing. It could be negative, which means you will see the autocorrelation going up and down, but the range is going down. So it's dying slowly. But on the other hand, the partial correlation is cutting off, meaning that you see a very strong autocorrelation probably in the first leg or the second leg, and then nothing afterwards, or virtually nothing afterwards. We call that kind of situation cutting off. Okay, so if autocorrelation is dying out and partial autocorrelation is cutting off, then it tells us we do need the AR part. And the number of significant autocorrelation in the partial autocorrelation graph tells you the number. If we see one significant autocorrelation, like 1 bar here, then that's the AR1. If we see 2 bars there, and for the rest of them, they're virtually 0, then that's the AR2 process. Okay, so that's the judgment for AR part. Now again, autocorrelation dying out, partial autocorrelation cutting off. Wherever it's cutting off, that's the level or the number for the AR part. All right, the MA part is just the opposite. If we observe that partial autocorrelation is dying out, meaning again the autocorrelation is decreasing gradually with the same sign, or dying out with the opposite sign, but the range is decreasing, then we say partial autocorrelation is dying out. On the other hand, autocorrelation cut off, right? So the autocorrelation could cut off at leg 1 or could cut off at leg 2. If that's the case, then we need MA part, moving average part, and wherever the autocorrelation legs are cutting off, that's the level of MA we need. And this is MA1, that is MA2. All right. Now, when do we need both? Well, here's a situation where we have both the AR part and the MA part. As you can see that autocorrelation and partial autocorrelation are dying out. Okay, there's no very apparent cutting off. So that's the case where we have both the AR part and MA part. And we can start with a 1-1 as a start point and see if the model is adequate. Now, the next slide shows you the autocorrelation and the partial autocorrelation side by side to determine what's the process we need. But I believe it might be helpful if I move to Minitab and show you how to obtain everything we talked so far. So I'm gonna switch to Minitab. So here we go. So the name of the file is Dow Jones. We have the time period. There should be 65 observations, and we also have the closing average. Okay. Typically, we do time series plot. So let's do that. Closing average is the series. Click OK. There we go. So that's the time series plot showing the upward trend. For sure, it's not stationary. I'm skipping the autocorrelation for this original data. Instead, let's do the difference. So we're going to take the difference of the data. I'm going to name there diff and go to calculator. And we're going to store the results in diff. Double click on it. For the expression, we want to use the function. If you go through the list, you will see difference here. Click select. We want to take the difference of the closing average. There's a brackets with leg asking you how many legs do you want to do. So we are taking the first difference and therefore we can omit that. That's the expression. Click OK. We got the difference. Now, starting from this point, we're going to use this column as our data to do the analysis. So we want to obtain the autocorrelation graph, which start from stat time series autocorrelation. We're taking difference data. Click OK to get the autocorrelation graph. Looks like this. For the partial autocorrelation, we still go to stat time series, and we're doing this guy, partial autocorrelation. So click on it. Same idea. We want to use the diff as the series and click OK. That's the partial autocorrelation. Similar to the autocorrelation graph, but the details are different. Okay, so that's how we obtain the graphs so far. At this point, I'm going to go back to the document because there we can look at the two graphs side by side to do the comparison to determine the AR part and the MA part. Okay, so here we go. Those are the graphs we have. The idea is we're going to need to determine which one is dying, which one is cutting off. It's not a very easy decision. There's no clear cut, right? It's not as nice as the ones we saw in theory, like what I showed you back here, right? For the AR part, I said if autocorrelation is dying, partial autocorrelation is cutting off, then we have an AR process. If we have the opposite, then we have an MA process. These are theories. They look very clear. It's very clean. However, when you look at the reality, you probably will say, oh my goodness, this is nothing close to what the theory says, right? So that's actually the tough part. That is, we need to determine whether autocorrelation is cutting off or dying off. I would say at this point, there's no specific answer. It could be both. I could argue that autocorrelation is dying off because I do see gradually these bars are decreasing. On the other hand, I could say partial autocorrelation is cutting off at leg 1 because there's no autocorrelation for leg 2. Then we have autocorrelation for leg 3. So one way to say is autocorrelation dying off, partial autocorrelation cutting off at leg 1. If that's the case, then going back to the theory, keep in mind autocorrelation dying off, partial autocorrelation cutting off. Then we have an AR process, right? So we could take that as one model. We have AR1, right? On the other hand, I can also argue that partial autocorrelation dying off and autocorrelation cutting off at leg 1 because leg 1 is the one that's significant. If that's the case, then we have an MA1 process. And we do want to try both models to see which one is better because at this point, we don't have a clear answer. Either one may work, okay? And apparently, we took the first difference. So we also have the integrated component, which is I1. And therefore, putting all the information together, we could try ARIMA 110 or ARIMA 011, meaning we have integrated one, we have either AR1 or MA1. So that's the idea. Now the next step is to estimate the ARIMA model for both of them using Minitab, and then to determine which model gives us a better fit or which model is more adequate. I do not want to switch back and forth between this PowerPoint slides and Minitab. So let me postpone that for a little bit and let's look at the results from Minitab. These two models, ARIMA 110, ARIMA 011. How do we determine which one's better? So one criteria we want to use is this MS part, mean squares. So mean squares kind of measuring the deviation between your estimation or your forecast versus the original data, okay? And the smaller MS means a better model, all right? The smaller MS is, the better. So when looking at these two models, there's not really any difference. One is 3.536 and the other one is 3.538. Tiny little bit difference. So I would say both models are good. And the other item we usually check is this Box-Pierce chi-square statistics. It's another test helping us to determine if the model is adequate or not. Chi-square test, we're still looking at p-value. If the p-value is less than 0.05, then that means there's still significant autocorrelation. So the model will not be good enough for us to use. Okay, that's the other criteria. And again, the first criteria is to look at the mean squares. The smaller, the better. So let's go back to the results and see. There we go. In the output, it gave us the chi-square test for until the 48 lag. And by looking at the p-values, all of them are higher than 0.05, meaning that there's no autocorrelation in the residues. And therefore, both models are adequate. And based on the MS criteria, the two models are virtually the same. And therefore, it's okay for us to use either model for forecasting. And that leads us to the one last step, which is to check the residues. We're okay with both criteria. Now let's double check. We look at the residues to determine if there's still any significant autocorrelation going on that we need to deal with. By looking at the residual plot for both, we don't observe any significant correlation, meaning that all of the bars are within the right curve, and therefore the residuals are good as well. Now at this point, we do not need to repeat the process since we do find good models for forecast, and therefore we can continue with the forecasting. Here we want to forecast for the next period, which is period 66, because we had 65 observations. And then using Minitab, we can do the forecast to get the forecast for that period, as well as a 95% confidence interval. Okay, before I conclude, I want to move to Minitab and show you how to run the ARIMA model. All right, so let's estimate our ARIMA models. We want to go to Stat and go to Time Series, then move to ARIMA. Okay, the series we want to use is the original one because the ARIMA model we're going to estimate is ARIMA 110, which I've already put here. And Minitab will take the difference for us automatically. We took the difference at the beginning to make sure it's an integrated one process. We only need to take the first difference to make it stable. Since we're estimating the AR1 process, we put 1 for autoregressive, we put 1 for difference, and we put 0 for moving average. That's our ARIMA 110 model. All right. And since we're going to examine the residual later on, so you do need to click on storage and make sure residual is checked. So click OK, OK again. There we go. So several items we looked at previously. One is the MS value, which is 3.535. That tells us the deviation between our prediction and the original data. The other item we'll look at is the chi-square statistics p-value. They're all about 5%, which is good. Since we are here, let's check on the residual right away. For residuals, we want to do the autocorrelation graph. So you want to go to Stat, Time Series, Autocorrelation. And now this time, check on the residues to make sure there's no autocorrelation in the residues anymore after the model, which is the case here. So that means the model is adequate. The other model we want to estimate is the ARIMA 011 model, where we have the MA1 part. Okay, so let's do that. Go to Stat, Time Series, ARIMA again. Now we only need to change the autoregressive to 0 and the moving average to 1. That will give us the ARIMA 011 model. Everything else stays the same, so I just need to click OK to get the new model. Checking on mean squares, 3.5378, which is very similar to the previous one. Now, lastly, we want to check on the residues. So we go back to Stat, Time Series, Autocorrelation. And then this time is the second residual, the last residual we had. Click OK. And again, there's no autocorrelation in the residues anymore. So the second model is also adequate. Now, I'm going to start with another example. We're going to repeat the same process. And this is for you to have more practice and more understanding about how we select a ARIMA model from the family of models. Okay, let's get started with the second example. The analyst for Atron Corporation, Jim White, had a time series of readings for an industrial process that needed to be focused. The readings are plotted in the figure below. Jim believed that the Brooks-Jenkins methodology might work best for these data. And by the way, I've been talking about ARIMA model the whole time. The other name for that model is called the Brooks-Jenkins methodology. So here is the time series plot for the readings. As you can tell, this process is stationary because we don't observe any trend. We don't really observe any pattern. So that tells us we don't need to take the first difference. For the integrated level I, it is 0. After that, what we need to do is to obtain the autocorrelation graph and the partial autocorrelation graph to determine the levels, right? So here we go. These are the two graphs. The first one is autocorrelation, and the second one is the partial autocorrelation. So to determine the levels for the AR part and MA part, let's see. The idea is we want to determine in which graph we have dying off and which graph we have cut off, right? So let me go back to the theory to give you some review. Here we go. So when we look at the two graphs, we're trying to determine if the autocorrelation is dying off, like what you see in this graph, or the autocorrelation is cutting off, like what you see here. When we say cut off, that means we basically see one major autocorrelation, and then for the rest, they're virtually 0. Of course, we sometimes don't really get 0, but they're pretty much close to 0. And for dying off, what we would observe is the autocorrelation is decreasing gradually over the lags. Okay, and when we observe dying off in autocorrelation, but cut off in partial autocorrelation, that tells us that we have an AR process. And based on the cutoff lags, we determine the level for AR process. Now, on the other hand, if we have autocorrelation cutting off in autocorrelation graph, but dying off in partial autocorrelation graph, then we determine we have a MA process, moving average process. And again, the level is determined by lags that's cut off in the autocorrelation graph. So for this one, that's MA1, and for this one, that's MA2. All right, so let's go back to our graphs. And same as the previous example, a lot of times when we look at the graphs, we don't really have a clear cutoff and tell us, oh, this is absolutely an AR process, this is absolutely an MA process. So for these two graphs, at least it's hard for me to say which one is really dying off and which one is cutting off. So what we usually do is to try both. We're gonna say autocorrelation is dying off and partial autocorrelation is cutting off. If we decide that the partial autocorrelation is cutting off after leg 1, which makes sense because leg 1 is significant and the rest of the autocorrelation are much smaller, then we can say we have an AR1 process. Or if we use ARIMA, the parameters are 1, 0, 0. So it's ARIMA 1, 0, 0. The other option is to say that the autocorrelation function is cutting off and the partial autocorrelation function is dying out. And now let's look at the autocorrelation function and decide what is the parameter. What we can see is that the first 2 legs are relatively higher than the rest. In particular, leg 3 is virtually 0 and leg 4 is 0. So we can say autocorrelation is cutting off at leg 2, and therefore we have an MA2 process. Or if we want to write it as ARIMA, that will be 0, 0, 2. That's the parameters for ARIMA. Now, if we fit the 2 models to the data in Minitab, we will get the following results. I'm going to show you how to do everything in Minitab after we review the results as well as checking the residues. So let's examine the results first. 2 models again, AR1 process and the MA2 process. The 2 criteria we usually look are the MS values, mean squares values, and the P values for the chi-square test statistic. In terms of the mean squares values, for AR1, it is 137.9, and for MA2, it is 135.07. MA2 is slightly better than the AR1 process. There's only about 2 units difference, not big deal. In terms of the p-values for the chi-square test statistic, they are all greater than 5%, indicating that we don't have any zero correlation. And therefore, both models are good. Both models are adequate. Now, if we want to pick one for focused, you might say, well, the MA2 process should be picked because the MS value is a little bit lower than that for the AR1 process. However, there's another criteria that people usually use in practice. That is, we usually prefer a simpler model than a more complicated model. One reason is that in more complicated model, we may introduce more noise. So in our case here, actually, we're gonna pick the AR1 process, and the term for that principle is parsimony. We'll have the principle parsimony, meaning that we will always prefer a simpler model than a more complicated one with other things equal or other things very similar. Now, ideally, we should have checked the residues before picking AR1 process. So let's check the residues now. Here I have the ACF for the residues for both models. As you can see, we don't observe any significant autocorrelation in the residues, and therefore both models are confirmed to be adequate. Now back again, we're gonna pick the AR1 process. All right, next I'm gonna move to Minitab and show you how we carry out the analysis for this example. The name of the file is Astron process. Number 1, we're gonna do time series plot of the original data to examine whether it's stationary or not. So we go to stat, time series plot, pick the simple one. The variable is readings, click OK. As we just discussed, this process is stationary, so the integrity part is a level of 0. Next, we want to obtain both the ACF and the partial autocorrelation. So we go back to stat, time series, autocorrelation. Series is readings, click OK. That's the autocorrelation function for the original data. We also need the partial autocorrelation function. So we'll go back to stat, time series, partial autocorrelation right here. Again, readings is the series, so click OK, and that's the partial autocorrelation function graph for the original data. Then we decided we're gonna use an AR1 process and also an MA2 process. So let's fit these two models. We're gonna go back to stat, time series, and pick ARIMA. Series is still readings, and let's go with AR1 first. So we're gonna put 1 for autoregressive, 0 for difference, 0 for moving average. We will store residues since we're gonna examine the residues at the end. So click OK. OK again. That's our AR1 process. And next we will do MA2. So go to stat, time series, ARIMA. And this time autoregressive is 0. Moving average is 2. We still want the residues is already selected previously. So click OK. We've got the MA2 process. Lastly, we also obtained the ACF for the residues. So we'll go back to stat, time series, and this time we want to do autocorrelation only for the first residue. So click on the residues and click OK. That's the autocorrelation function for the first residue, the AR1 process. Similarly, we go back to stat, time series, and pick autocorrelation. We can check the second residue. So it's residue 1, click OK. And that's the ACF for the second residue for MA2. All right. So these are all the steps you need to carry out. Of course, since we discussed the results already, I didn't go through them in details. In practice, we will examine each graph carefully, then move to the next step. So now let's return back to our PowerPoint slides. This is the very last topic we have for the entire semester. That is, we're gonna learn how to use ARIMA models for seasonal data. Seasonal data is quite special because they have trend sometimes, they also have seasonality. And it is not just an AR1 process or MA process, it's not the same as we did before. We're gonna start the discussion with an example. It says here, Kathy Fisher was given the responsibility for forecasting sales for the Keytron Corporation. Kathy was able to collect 115 consecutive months of sales data. The data began in January 1997. Kathy examined the time series plot and noticed the pronounced seasonal pattern along with a general upward trend. She felt the series was non-stationary and decided to develop a seasonal ARIMA model for her data. All right. Now I've got the time series plot for the original data and also the autocorrelation for the original data. We can see clearly that there is both trend and very strong seasonality in the data. This is also confirmed by the ACF function, which shows us that the first leg is significant, then the legs are declining gradually. Also notice that the 12th leg is very high. It is even higher than the first leg. Since this is monthly data, we know the 12th leg indicates seasonality. So it is confirmed her thought that the data is not stationary and we have trend and seasonality. Now, since the data is not stationary, we definitely need to detect the difference. So next step is to take the difference of the data. However, since we've determined that it is monthly data and we know the pattern repeats itself every 12 months, when we take the difference, actually, we're gonna take the 12th difference. You'd notice that in this screenshot, the lag is 12 instead of being omitted as before. I'm gonna show this in Minitab after we discuss everything here, but that's what we see. All right, after taking the difference, we've got this new time series plot. It seems to be stationary so far. Now we are ready to examine the autocorrelation and the partial autocorrelation to determine the levels for the AR part and MA part. So here we've got both of the graphs, the ACF and the partial ACF. All right, let's determine which one is dying out and which one is cutting off. To determine that, actually, we don't look at like 1, 2, 3, 4 anymore. We actually look at the seasonal lags, like number 12 and number 24, and determine if these lags are cutting off or dying out. Now, if you look at the autocorrelation function back here, lag 12 is significant, but lag 24 is not significant anymore. In comparison, for the partial autocorrelation, lag 12 is significant, lag 24 is also significant. Therefore, we can say that for the partial autocorrelation, it is dying out because it didn't reduce to non-significant directly. It's declining gradually. But for autocorrelation, we can say it is cutting off because only the first seasonal lag number 12 is significant, and then when we move to lag 24, it is insignificant already. And therefore, we are looking at a MA1 process. Remember, for partial autocorrelation dying out, autocorrelation cutting off, that's an MA process. And this is how we denote the process. It's not ARIMA 011. Actually, we add another level of parameters back here, and we use 12 as a subscript to denote that this is seasonal data, and the seasonal lag is 12, all right? So that's the complete specification for this ARIMA model. It's ARIMA 000, meaning at the level, they're all 0. Then for the seasonal components, we have 0, 1, 1. Now, if we fit this model in Minitab, we'll get the following results. We have all the p-values, again, are greater than 5%, and therefore we can tell there's no serial correlation. Lastly, we will examine the residues, and here's the autocorrelation function for the residues. I would notice that there's still at like 3, it is slightly higher than the red curve, meaning it's significant. We can either keep trying other models to see if we can capture that significance, or since it's indicated by the chi-square test statistic, the model is adequate, we can go ahead and use the model to do the forecast. And here's the forecast results. So next, I'm gonna move to Minitab and show you how to carry out all of these analysis, and then we will wrap up. All right, so here's the Minitab. This time, let's go through everything. So I'm gonna start with a time series plot of the original data. Okay, so basically I did stat, time series, and time series plot. So that's the plot of the original data. We can see both strong seasonality and an upward trend. We can also get go to stat, time series, autocorrelation to get the autocorrelation of the original data to double check and confirms that there is trend because the autocorrelation is dying out gradually. And there's also strong seasonality because there's high autocorrelation at the lag 12 and lag 24. So that confirms that we do need to take the first difference to make the data stable. Okay, what we do is actually we take the difference at the 12th lag, meaning we're taking the current period value minus the value 12 period ago. I'm gonna define a new variable diff and then go to calculator. The value will be stayed in diff and function or expression will be differences. We're taking the differences of sales, double click on sales. Now this time we do need to specify the lag. In the past, when we take the first difference means then we can omit it because that's default. Now this time we want to take the 12 period difference. So we need to define the lag to be 12. Okay, so that's the big difference for this example. So 12 month, we do 12, but if it's quarterly data, we will put 4 there. Okay, so click OK to get the difference. And don't worry if you see the stars there, it just means you can't take difference for the first 12 values. It starts from the 13th because when I said you take the value of the current period minus value 12 period ago, you need 13 period to do that. So this 20.8 is basically 1757.6 minus the very first value 1736.8. All right, so next step we're gonna do time series plot again to examine if the first difference take care of the trend. Okay, so this time we'll take the series as diff and click OK. So that's the new time series plot for the difference data. I don't see any specific trend here. Then we can decide using autocorrelation graph and the partial autocorrelation graph to determine what we want for the ARIMA model specification. We know for the I part, we're gonna take the first difference for the seasonal data, right? So let's see, we can go to stat, time series. We can get the autocorrelation of the difference, all right? So there we go. We need to have the partial autocorrelation for the difference data and click OK. All right, so that's the partial autocorrelation. When we were going through the PowerPoint slides, we determined that the partial correlation is dying out because it's significant at like 12 and 24 and probably 36, which we don't have for the current graph. Now going back to the autocorrelation graph, it's definitely cutting off at like 1 or like 12, the first round of the seasonality, because it's not significant at like 24, right? So that allows us to determine the model to be an MA process. Now the next step is to estimate our ARIMA model. Go to stat, time series, and pick ARIMA. The series will be the sales. We don't need to take the difference. Minitab will take care of that. And we need to specify we're fitting a seasonal model. So check fit seasonal model box. And the period is 12 because this is monthly data. Now, remember the specification of ARIMA is 000. That specifies for the non-seasonal part. For the seasonal part, we have 0, 1, and 1 to specify an MA process, and we took the first difference. And notice that the difference, we put 1 for the seasonal section, but non-seasonal section, we put 0. And this is because we took the difference at the 12th lag, right? We didn't take current period value minus previous period value. Instead, we took current period value minus 12 period ago. That's why we put 1 in the seasonal section, so that Minitab knows it takes difference between current period versus 12 period ago. All right. Now that we are here, we're gonna get the residue. Okay. And remember, At the end, we want focused. It just really depends on how many periods you want to focus. For this example, the PowerPoint shows 1, so we're gonna do 1. You can do 3, of course, it doesn't hurt. So click OK and click OK to get the estimate, right? By looking at the mean squares again, it's 11,610. It's not very small in comparison to some of the other examples we looked at. But since this is the model we picked, we're not using that to compare with anything. We'll just leave it like that. The p-value are all greater than 0.05, meaning that there's no significant correlation for the residues. And also we have the focus there. The value to be 2419, that's the sales for the next period with a 95 limit between 22,008 and 2630. Lastly, we typically look at the residues to double check. So this time I'm gonna do the autocorrelation for the residues and just to take a look. So there we go. For the residues, the lag at the 4th period is slightly significant. This is something we can address using other more advanced techniques. But in terms of using the seasonal REMA based on p-values we saw from the results, we're gonna still conclude that the model is adequate. So that's it. That's all we have for this chapter, and that's all we have for this semester's formal lecture. Email me if you have any questions.